The only point to which I wish to draw attention is the following. In this calculation I had occasion to rest my case on only two facts, namely, that the first and second derivatives of the logarithm remain, in the interval considered, between certain limits. Hence our first conclusion is that the property is not only true of the logarithm, but of any continuous function whatever, since the derivatives of every continuous function are limited. If I was certain beforehand of the result, it is because I have often observed analogous facts for other continuous functions, and next, it is because I went through in my mind in a more or less unconscious and imperfect manner the reasoning which led me to the preceding inequalities, just as a skilled calculator, before finishing his multiplication, takes into account what it ought to come to approximately. And besides, since what I call my intuition was only an incomplete summary of a piece of true reasoning, it is clear that observation has confirmed my predictions, and that the objective and subjective probabilities are in agreement. As a third example I shall choose the following. The number u is taken at random, and n is given very large integer. What is the mean value of sin nu? This problem has no meaning by itself. To give it one, a convention is required. Namely, we agree that the probability for the number u to lie between a and a plus dA is function of a dA, that it is therefore proportional to the infinitely small interval dA, and is equal to this multiplied by a function of a, only depending on a. As for this function I choose it arbitrarily, but I must assume it to be continuous. The value of sin nu remaining the same when u increases by 2p, I may without loss of generality assume that u lies between 0 and 2, and I shall thus be led to suppose that a is a periodic function whose period is 2, and I shall thus be led to suppose that a is a periodic function whose period is 2p. The mean value that we seek is readily expressed by a simple integral, and it is easy to show that this integral is smaller than 2m sub k divided by n to the kth power, m sub k being the maximum value of the kth derivative of u. We see then that if the kth derivative is finite, our mean value will tend towards 0 when it increases indefinitely, and that more rapidly than 1 divided by n to the k minus 1 power. The mean value of sin nu when n is very large is therefore 0. To define this value I required a convention, but the result remains the same whatever that convention may be. I have imposed upon myself but slight restrictions when I assumed that the function a is continuous and periodic, and these hypotheses are so natural that we may ask ourselves how they can be escaped. Examination of the three preceding examples, so different in all respects, has already given us a glimpse on the one hand of the role of what philosophers call the principle of sufficient reason, and on the other hand of the importance of the fact that certain properties are common to all continuous functions. The study of probability in the physical sciences will lead us to the same result. 3. Probabilities in the physical sciences. We now come to the problems which are connected with what I have called the second degree of ignorance, namely, those in which we know the law but do not know the initial state of the system. I could multiply examples, but I shall take only one. What is the probable present distribution of the minor planets on the zodiac? We know they obey the laws of Kepler. We may even, without changing the nature of the problem, suppose that their orbits are circular and situated in the same plane, a plane which we are given. On the other hand, we know absolutely nothing about their initial distribution. However, we do not hesitate to affirm that this distribution is now nearly uniform. Why? Let B be the longitude of a minor planet in the initial epoch, that is to say, the epoch 0. Let A be its mean motion. Its longitude at the present time, i.e., at the time t, will be AT plus B. To say that the present distribution is uniform is to say that the mean value of the sines and cosines of multiples of AT plus B is 0. Why do we assert this? Let us represent our minor planet by a point in a plane, namely, the point whose coordinates are A and B. All these representative points will be contained in a certain region of the plane, but as they are very numerous, this region will appear dotted with points. We know nothing else about the distribution of the points. Now what do we do when we apply the calculus of probabilities to such a question as this? What is the probability that one or more representative points may be found in a certain portion of the plane? In our ignorance, we are compelled to make an arbitrary hypothesis. To explain the nature of this hypothesis, I may be allowed to use, instead of a mathematical formula, a crude but concrete image. Let us suppose that over the surface of our plane has been spread imaginary matter, the density of which is variable, but varies continuously. We shall then agree to say that the probable number of representative points to be found on a certain portion of the plane is proportional to the quantity of this imaginary matter which is found there. If there are, then, two regions of the plane of the same extent, the probabilities that a representative point of one of our minor planets is in one or other of these regions will be as the mean densities of the imaginary matter in one or other of the regions. Here then are two distributions, one real, in which the representative points are very numerous, very close together, but discrete, like the molecules of matter in the atomic hypothesis; the other remote from reality, in which our representative points are replaced by imaginary continuous matter. We know that the latter cannot be real, but we are forced to adopt it through our ignorance. If, again, we had some idea of the real distribution of the representative points, we could arrange it so that in a region of some extent the density of this imaginary continuous matter may be nearly proportional to the number of representative points, or, if it is preferred, to the number of atoms which are contained in that region. Even that is impossible, and our ignorance is so great that we are forced to choose arbitrarily the function which defines the density of our imaginary matter. We shall be compelled to adopt a hypothesis from which we can hardly get away. We shall suppose that this function is continuous. That is sufficient, as we shall see, to enable us to reach our conclusion. What is at the instant t the probable distribution of the minor planets? Or rather, what is the mean value of the sine of the longitude at the moment t, i.e. of sine AT plus B? We made at the outset an arbitrary convention, but if we adopt it, this probable value is entirely defined. Let us decompose the plane into elements of surface. Consider the value of sine of AT plus B at the center of each of these elements. Multiply this value by the surface of the element and by the corresponding density of the imaginary matter. Let us then take the sum of all the elements of the plane. This sum, by definition, will be the probable mean value we seek, which will thus be expressed by a double integral. It may be thought at first that this mean value depends on the choice of the function, phi, which defines the density of the imaginary matter, and as this function, phi, is arbitrary, we can, according to the arbitrary choice which we make, obtain a certain mean value. But this is not the case. A simple calculation shows us that our double integral decreases very rapidly as f increases. Thus I cannot tell what hypothesis to make as to the probability of this or that